Hi everyone, my name's Dan Draper and I'm the CEO and founder at SafeStash, and today I'm going to be talking about practical attacks on encrypted databases. So the first question you might ask yourself is, why do we actually bother to encrypt a database? What kinds of things are we protecting ourselves from? So there are some threats to consider as to why we would want to encrypt a database. Number one is, let's say we're afraid of an attacker who learns the database connection string. There's only one database connection string for a database typically, and if that's breached, then a user could potentially get access to the database. We might be concerned about an attacker who gains access to the host server, the actual machine where the database is running. We might be afraid of an attacker who retrieves a database dump or a backup. That's actually relatively easy to achieve in many cases and quite common. And one final one, which we often don't tend to think about, is a trusted user, an insider. In this case, a trusted database administrator who maybe we want to be able to access the database, but not necessarily be able to read all of the data stored in the tables. Before we go on, I wanted to make a quick mention to Assistant Professor Paul Grubbs, who was the co-author of a paper from back in 2017 called Why Your Encrypted Database Is Not Secure. A lot of the work in this talk is based on that paper and trying to take a more practical approach so that it's accessible to a wider audience. But certainly a big thanks goes out to Paul and his co-authors for writing that paper. So given this, what leads to exploits? Certainly one of the major things is this idea of a query cache. Things like MySQL and PostgreSQL use query caches quite heavily for performance, but that can leak information leading to an attack. Logs, query logs, system logs, write-ahead logs. Many databases use this idea of a write-ahead log to ensure consistency and reliability, but that comes with the potential to reveal information to an attacker. An obvious one, but worth stating nonetheless, is poor key management. Poor key management is true of any cryptographic system, and no less in this case. Shortcomings in the cryptography itself, and we'll talk more about that and some examples of shortcomings like those in this talk. Certainly that's a major part of why data is lost. And finally, poor assumptions about data sensitivity. What kinds of data should we actually consider to be secret? What kinds of data might we be thinking of quite innocuous but could lead to leverage for an attacker? And I would also like to mention that the techniques and attacks in this talk, please use for good. Don't just go start attacking random servers or databases on the internet. It's probably illegal and not really a nice thing to do. So use this just for your own educational purposes or in test environments only, please. Right, let's get started with the first kind of encryption that I want to talk about today, which is called transparent data encryption. Now, this is the formal name for what we often refer to as encryption at rest. So what is encryption at rest or transparent data encryption? Transparent data encryption is encrypting the file system for the machine where the database is running. And so because when the database boots up, it needs to get access to the data, it also means that the keys to perform the decryption need to run on the same machine. And actually, all the data that the data needs to manage gets loaded into memory and is available in the clear. So transparent data encryption actually doesn't protect us from a whole lot. Certainly if an attacker gets access to the machine itself, the host, or even the application that's accessing that database, transparent data encryption doesn't protect us. And what I wanted to do is just show a very simple attack that demonstrates really how useless TDE is in practice. And that is through this idea of SQL injection. So really nice, simple, easy attack to get us started. You've probably heard of SQL injection. If you haven't, I'm about to show you what it is. We'll get into some more interesting attacks and advanced attacks later in the talk. With a SQL injection attack, I actually don't need access to the client or application, and I don't need access to the database host. All I need is the ability to enter particularly crafted queries, and for the developer of the application that I'm querying to have not sanitized their inputs properly. And this is a very common, sadly still very common problem in our industry. So I've created a PostgreSQL instance in Amazon's RDS, that's their relational data service. And you can see from the configuration here that I've enabled encryption. This configuration is in the storage section. So Amazon are trying to make it clear that this is only applying to the file system and not to all of the data stored. Nonetheless, a lot of people assume that TDE is going to protect them for a whole bunch of things, which it won't. So if we jump into the database console now using PSQL, you can see I've got a few tables here, and I can just do selects on the data like there's no encryption whatsoever. This is a products database that I've created just for a simple, e-commerce application written in Ruby on Rails. And I've got a products table, as you can see, and a customers table. One feature in this application is a search capability. Very common for an e-commerce application. I've got some products in here that I want to search. I'm a big fan of Sony cameras, so I'm going to search for Sony, and you can see the results come back. Now I'm going to exploit this search bar to do a SQL injection attack. First thing I want to do is find a query that prevents any search results, product search results coming back. So I'm going to find a query that matches nothing, and that's XX. That gives me no results. So let's start with that. Then what I'm going to do is close the quote so that that signals to the database that that's the end of the constraint. And I'm going to union those results with a query that is the same shape as the products query. So, but this time it's going to come from a different table. So I'm going to select from name, email, and I'm going to say as description, so that the union query thinks it's the same shape data. From customers, I'm going to end that query as I normally would, and then I'm going to use this dash syntax, which signals to the database query parser that everything after that should be treated as a comment and essentially ignored. And so that means that if there were anything else left in the query after this input string, it'll basically get ignored. So my code here will take precedence. So let's see what happens. Okay, I run that and I get all of the customers instead of the products. And as you can see, this is a very simple example of a SQL injection attack, but the point here is that transparent data encryption protected us from nothing. Okay, so what if an attacker does have access to the host server? How can we protect ourselves? Maybe they've got access through a remote code execution, or maybe they're even a trusted insider or a semi-trusted insider. One technique we can use in the PostgreSQL ecosystem is called pgcrypto. It's an extension that adds some additional functions. So how does it work? pgcrypto provides a whole bunch of functions, but one example is the pgp sim encrypt function. pgp sim encrypt uses the pretty good privacy library underneath the hood, performs a symmetric encryption using a pre-shared key, and in this case I'm using it to encrypt my name and email address for the data that I'm storing in the table. So I've created a little demonstration database here called pgcrypto demo. Just has a users table inside it, and when I query the users table, you can see that everything inside that table has been encrypted. So if an attacker was able to get access to this database, in theory they wouldn't be able to get access to any of the underlying information. It's been fully encrypted by this pgcrypto library. But I'm going to show you how to attack it. So attack 2, direct memory access. In this attack, as mentioned, this relies on the attacker getting access to the database host that's been compromised. So to demonstrate this attack, I've set up my Mac on my right-hand side here, and I'm going to connect to the database running on my Linux box, which is on my left-hand side, and show you that I can actually extract some of the information over the wire as it's being inserted. To do that, I'm going to use a tool called AVML, or Acquire Volatile Memory for Linux. Ironically, this tool has actually been created by Microsoft. It's been very useful in these kinds of tests. So the first thing I'm going to do is go over to my Mac here and connect to my Linux box on my local network and connect to the pgcrypto demo database. Okay, you can see it's got the same users table in it. So I'm going to run a query that I ran before. This is going to insert into the users table name and email. It's going to use that PGP sim encrypt function that we talked about before. It's just going to encrypt the name here at Homer Simpson with the same key, and the email homer@springfield.com once again with the same key. So I'm going to run that insert, and then when we select from the users table, you can see that now there are 2 rows and they're fully encrypted. I can't see any information. Now what I'm going to do is take advantage of the fact that Postgres stores some of these queries in a query cache. So using the AVML tool on my Linux box, which is hosting the database, I'm going to run as root using sudo AVML, and then I'm going to push the output onto one of my local drives here, avml.lime. This is going to take a while to run. Thankfully this is pre-recorded, so we can skip ahead to the end. Okay, so that's just finished. My machine here is has 64 gig of memory, so it took about 6 or 7 minutes. Now I have this file on my B volume here called avml.lime. Lime is a particular format and there are tools that can read it, but we actually don't need to use any of those tools. We can do something really just brutal and nasty. So I'm actually just going to cat and grep this AVML file. I'm using a grep alternative here called Silver Surfer, which is a bit faster, but same basic idea. And I'm actually going to search, just for illustrative purposes, for the query that we inserted, or the data that we inserted before, which was homer@springfield.com. Now remember that this is running on the database machine, and the query was actually performed from my Mac. Just going to kill that. You can see here that the exact command I used on the Mac to do that insertion was stored in a query cache in Postgres on the server. So immediately I've now got access to the key. Now if I didn't know what data to grep for, I didn't know what had been inserted, I could actually just grep for, say, a regex of a hex encoded string, which would give me a key. There's all kinds of different things you can do. So I can search for, let's go PGP sim encrypt. Oops. And as you can see, there's all of the previous attempts at getting this working coming through in the logs. So really this is quite terrifying and a pretty clear demonstration that tools like pgcrypto are actually not as safe and secure as you might think. And that's because you're sending the keys across the wire via PSQL to be processed on the server side. And because of the way Postgres query caching works, a lot of that data gets stored, and potentially for really quite a long time. So we need to do something better. All right, so let's look at a third class of encryption. And this is called deterministic encryption. So deterministic encryption is essentially the idea that every time we encrypt a particular value, or a plaintext if you like, with a given key, we'll always get the same result. So in this case, I've got the encryption of cat under the key K. We get that ciphertext. Dog gives me a different one, obviously, but I encrypt cat again and I get the same ciphertext output. And so that's what makes it deterministic. It's always going to be the same output value. Now, why would we do that? Why is that a good thing? Why is it useful? Let's say we want to look at a database like this, where we're keeping email addresses stored using deterministic encryption in the table. Let's say we want to look up a person based on the email address. We don't want to send the email address to the server, as we've seen in the previous attack. That can be problematic. So we actually want to hash or use a deterministic encryption scheme to encrypt the email address first before performing the query, and just do the query on the ciphertext rather than on the plaintext. So it can be very useful. However, deterministic encryption has some pretty major drawbacks. There was a study from some researchers in 2015, Naveed et al., and I'll provide a link at the end of the talk, that showed that deterministic encryption schemes are vulnerable to what's known as inference attacks. So that's when the distribution of the ciphertexts mirrors or is closely related to the distribution of the plaintexts. So you can see in this bottom example, for a Gaussian distribution of data, the output domain looks very, very similar to the input domain in terms of the distribution. A really simple way to visualize that, if you've done any cryptography before, I'm sure you've seen this image. When you have an output distribution that looks the same shape, has a similar distribution to the input distribution, it doesn't really hide anything. You can use statistical methods, and in this case, just visual inspection to see that the encryption hasn't really worked. What we want is randomized encryption, but we'll come to that later. So, attack number 3. But actually, I'm not going to do an inference attack. I'm going to do another kind of attack on deterministic encryption schemes called a chosen plaintext attack. This kind of attack relies on the attacker being able to see the results of the system encrypting particular plaintexts or particular values that we want to experiment with, that we want to test. There's lots of different ways you could do that. Certainly if an attacker got access to the database host itself, they could do that. But I'm actually going to use the database write-ahead log and a previous, like an older database backup that I've managed to extract from a compromised NFS server. So here's my copy of the database dump. It's for a medical application. I've already imported that into a database here called Medical App Development. You can see it's got quite a bit of data in it. And let's take a look at the patients table. As you can see, all of that data is encrypted. It's unintelligible. So all of this data was encrypted using in a Ruby on Rails application using the encrypted record function. So that has a particular format. It wraps the ciphertext and the related information inside JSON. You can also see that there's a prescriptions table. Now the prescriptions table is not encrypted. Instead, what this does is link a patient ID, which has obviously encrypted information associated with it, just to a drug name. So we want to see if we can work out if a particular individual is taking a particular kind of drug. Okay, so now to do this, I'm actually going to go to the public part of this medical application. It's running on my local machine here for demonstration purposes, but in practice this would be running on a public website somewhere, and I'm going to go and create an appointment for the user that I'm interested in learning more information about. So on the new appointment screen, I'm going to enter the email address of the user, and I'm going to set an appointment. Doesn't matter when. Just do it at 2:25 in the morning, and go ahead and create this appointment. Now, as I previously mentioned, I've been able to get access to the write-ahead logs for the database that's powering this application. So I'm going to take advantage of that fact now. I know that because this is a Rails application and it's using encrypted record, I know the format for the ciphertext, or at least for the IV part of the ciphertext, is base64 encoded. So I'm going to grep for base64 encoded strings inside the write-ahead log. So I've got my write-ahead logs available here. I'm going to cat them. I'm going to grep for a regular expression that matches, or should match, a base64 encoded string of at least 12 characters long. And there we go, we've got a few of them. Now the latest one, and looking for the IV, it's the initialization vector. So I'm going to use that IV value, which should be unique, to see if I can find the associated patient record and thus the medications that they're taking from my medical database. So to do that, I'm going to use a query that looks a bit like this. So we know that the data is going to be stored as a JSON string. That's how Rails stores the data. So we're going to use PostgreSQL's JSON functions here. We're going to extract the initialization vector out of that JSON payload, and we're going to compare it to the string we found in the write-ahead log. So remember, we're comparing this to the database dump that I've managed to steal. It was a few days old. And yes, we found a matching record. So you can see the JSON here, the way that encrypted record stores it. It's got this hash key with the IV, and that's the IV that we found in the write-ahead log. And so now all I need to do is find the prescription, the user with that ID inside the prescriptions table. So 2749, and there we have it. So we can see this patient's been prescribed disulfiram, which, if you look it up, is actually a drug that helps people with alcohol dependency. So that would be considered pretty sensitive information, and we've just managed to get it despite the fact that the database has been fully encrypted and has been encrypted before it's been sent to the database server. I should mention that the way that Rails encryption does deterministic encryption is it uses a fixed IV. That's the initialization vector here, and that's what I was searching for in this case. All right, so we mentioned randomized encryption before. Deterministic encryption has issues. So let's go all in. Let's see how we can attack randomized encryption. So that is essentially the best possible encryption. So attack 4, we're going to use a reidentification attack. To perform this attack, we don't need access to either the client application or the DB host. All we need is a relatively recent dump of the database, like a backup. And actually, this would seem fairly feasible, because if the database has been encrypted using randomized encryption, the DBA may have just decided that an additional encryption step wasn't necessary because the data was already encrypted. In other words, the database dump may not necessarily be considered sensitive. So in this example, we're going to use a check-in app, something that everyone's probably very, very and painfully familiar with at the moment. And in this case, we've got two data types, one called a person, which is fully encrypted, and one called a location, which is also encrypted with a small caveat, which I'll come to in a moment. And to manage check-ins, we're literally just tracking in a check-in join table the person ID of the person who checked in and the location to which they're checking in. So the data might look something like this, but there is a big problem here, and the database designer or the application designer may never have realized how much of a problem this was. And it's a common problem. What's happened here is we've fully encrypted using a non-deterministic or a randomized scheme, the name of the location, as we have done for all the information we store about a person. But because we want to be able to do geospatial queries, the location table also has longitudes and latitudes stored in plaintext. And if we were to encrypt that data, we would no longer be able to do geospatial searches. So, for example, you've got an outbreak of COVID and you want to find all of the people that have checked into venues within, say, a 200-meter radius. I'm not sure if that's actually what health professionals do, but I can imagine that would be a useful kind of query. And actually, this idea of storing what seems to be not sensitive data in a database alongside sensitive data that's been encrypted is actually very common. But there's a major issue when it comes to location data in particular. There was a study back in 2013 that showed that only 4 unique points, what they call a trajectory for a person, are required to identify a unique individual. They can do that with 95% confidence. And so we're going to take advantage of that fact in this attack. Now, the way that we do that is by using a related data set. So actually, this is all hypothetical, of course, and not real, but in this example, in this demonstration, I've come across a data set that has been leaked from an online dating app. That online dating app was tracking location of all of its users. it wasn't encrypting the data. So now I have a data set that's been leaked to the dark web, say, with a person's email address and a whole set of longitudes and latitudes, their trajectories, if you like. Now, while this may be fabricated, this example, this is based on many real-world attacks. For example, there was a New York Times journalist a few years ago who was able to use an attack very similar to this to learn an enormous amount of information about people that they were profiling, and some of whom were even in the Office of the President of the United States. So it's a very real attack. This is just a demonstration showing something very similar. So as I mentioned, I was able to get a copy of the check-in app database dump, and so I've imported it into a database on my local machine here. You can see there's a few tables. You can see the location table and the people table and the check-ins table. If I have a look at the people table, you can see that all of that data is encrypted. Name and email address are both encrypted. It can be a little bit tricky to see if this is deterministic or randomized encryption. Generally speaking, if something is randomized, you should never see any repeating values. Whereas deterministic, you sometimes will see repeating values if there are repeating plaintext in the database. For the locations table, you can see that the location name is encrypted, but the longitudes and latitudes are not. Now, as I mentioned, I also have a reference data set from this dating site. You can see that this has just got a CSV of longitudes and latitudes mapped to email addresses of the user. First thing we might want to try is look for common data points from our reference CSV file in the check-in database dump restore. So let's try one. Let's try this first one here. I'm going to set the lat and the long values from the reference CSV row, and we don't find any values. Now, I'll let you in on a secret. There are no longs and lats here that match exactly. And this is actually quite a problem for longitudes and latitudes because they are very, very high precision numbers, and to find something that matches exactly can be very challenging. So we're going to use a concept called a geohash. And what a geohash does is it buckets a longitude and latitude down into a particular kind of cell of a certain precision, depending on how wide a range of locations we want to assess. So we're going to see if there are longs and lats from the reference dataset and the target dataset that fit into the same geohash, and use that as a proxy for being the same location. So I've written a little script in Ruby here, which loads the reference dataset and creates a hash of the reference email addresses along with all of their points, i.e. their trajectory. Then it iterates each person in my target database, the check-in app database, and tries to find a person that matches some of those points. Ideally 4 or 5 of those points before we have the sort of confidence, relative confidence that person is the same person. I'm just using this person similarity to function, which internally uses the geohashing technique to try and find matching points. Happy to share the source code for anyone who might be interested in having a look at it. So let's go ahead and run this code. So I'm going to call the correlate function. So I'm going to call this correlate script, and I'm going to pass it the reference CSV, which remember was the data from the leaked dating app. As you can see, it's starting to work through each of the records in the target database, and we can see that For ID record 1, there was no match, so we weren't able to learn who that person was. For ID 2, however, found 3 matching points. So that's a reasonable confidence level. That's probably 70% confident. That's this person here. Further down, we've got another person, record ID 4, that found 4 matching points. So that's really a very high confidence level, probably 95%, and continues to go through. You can see that a few were not found at all. Some had reasonable confidence. A few more had very high confidence. This one had 5, and so on and so forth. So this is a very naive approach. To go through 1,000 records would take quite a while. Certainly if you've got databases of hundreds of thousands or millions of records, this would be a very inefficient way to do it. There are much smarter techniques. For example, there's an algorithm called the Hungarian algorithm, which is from combinatorics, and that allows you to do things, that allows you to do tests like this much, much faster. There are also more sophisticated ways to assess similarity. I can look at not just the locations that a person has been, but what times of day they've been, what days of the week, how recently they've been versus, somebody that's been very recently to a location versus they hadn't been there for a while may indicate something about that person. So there are quite sophisticated techniques that really motivated attackers can start to apply. And we've taken advantage here of the fact that a very small amount of seemingly innocuous data was included in the database, despite the fact that all of the other data was encrypted. So what have we learned from these 4 attacks? Number 1, I think it's pretty clear, encryption is not a silver bullet, and that even a small advantage matters. Any small opportunity that an attacker has to gain an advantage will potentially give them access to data. Also, what's really interesting going through exercises like this is that you realize the security of your data can be limited by the security of systems you don't control. As soon as you have any information that is available to an attacker, they can cross-reference that with data that's been leaked from systems much less secure than yours. So how do we solve these problems? Well, number 1, generally speaking, the rule of thumb is always encrypt everything. And I mean everything you possibly can, with randomized encryption. So for example, AES running in GCM mode with a 256-bit key. That is really the best possible encryption available. We can use things like strong searchable encryption. And what I mean by strong is it should be randomized, non-deterministic. But that's actually really a very new technology. It's partly what we're working on at CipherStash, and isn't really generally available yet. But certainly these kinds of technologies are coming. And similarly with auto-revealing encryption and homomorphic encryption. These technologies promise to allow us to add encryption to systems in ways that we haven't been able to before. And in particular, for example, the case of the longitudes and latitudes that we left unencrypted because we wanted to do geospatial searches on them. Things like homomorphic and auto-revealing encryption allow us to fully encrypt those data points as well. So we really get the best of both worlds. And it really goes without saying, but I'll repeat it nonetheless, always use a threat model and get pen tests regularly from people who understand this space. So finally, I'll leave you with some resources. There's the paper from Paul Grubbs and his co-authors. There's a really interesting, relatively digestible video by a channel called Computer File on YouTube, which talks about this re-identification problem using location data. And then another paper by Naveed et al. From Brown that talks about inference attacks. It's a really interesting paper, quite heavy mathematically, but if you're interested in this kind of thing, it's a really good place to start. So thank you. I hope you enjoyed this talk and learned a few things about encrypted databases and some of the pitfalls. You can follow me on Twitter, Daniel Draper. Feel free to email me if you're interested in talking about this topic or if you want to learn more. And you can check me out at my workplace at cipherstash.com. Thanks for listening and talk to you soon.